Hello, everybody. Welcome back. In this week, we will be talking about mechanics of materials and specifically about shear stress due to transverse load. Also, this message is for everyone with an engineering degree from outside of the United States. If you are interested in evaluating your education in this country, I have put together a PDF guide with step-by-step instructions on how to do that. Just click the link below and you'll be able to download it for free. Now let's move on with today's problem. The I-shaped section shown below is subject to transverse shear force equal to 90 kips. Calculate the maximum shear stress at the elastic neutral axis. Okay, so right away, let's see and look in the FE handbook, the formula for the shear stress, and more exactly, the transverse shear stress. I'll go ahead and do a search here, transverse shear stress. And here we go. We are under the mechanics of materials. And here's our formula. Okay, let's write it down and start calculating and solving the problem. Shear stress equals to the shear force times Q, which is moment of area, over the moment of inertia times B, which is the width of the shape where the neutral axis is. Okay, let's see, what do we know so far? So we know that V equals to 90 kips. Let's calculate the moment of inertia. Or first, let's calculate the elastic neutral axis, or the centroid of this shape. So in order to do that, I will note this is area number 1, or the shape number 1. This is number 2. And here it's going to be area number 3. In order to calculate the centroid, I will draw this table. Here we're going to have the shapes, and then we'll have the area in inch squared. And then we will have the x coordinate in inches. We'll have the y coordinate in inches. We'll also have then the this product of area and the x coordinate, and the product of the area and the y coordinate. Let's follow along and do this. So area number 1. Let me grab my calculator and move on. So area number 1, 10 times 1 is going to be 10 inches. In order to calculate the centroid, we have to start by choosing an arbitrary datum. So I'm noticing that in this direction, the shape is actually symmetrical. So I will go straight to the middle. There you go. Here, and then this is going to be my x. Okay, so knowing that I'm going through the middle, my xe actually goes through the middle because the center of this shape, it's right on the y-axis, so the xe is equals 0. Now the y equals to this distance here, right? There you go. So this is going to be 1.5 plus 20 plus 0.5, and that equals 222. It's 20 plus 1.5 plus 0.5. Now this product, area times the x component is 0, and then the area times the y equals to 220. Let's go to area number 2. We have 20 times 3/4 equals to 15. The same thing here. X component is going to be 0, and then the y is going from the middle of this shape all the way to the bottom of this flange here. So we have 10 plus 1.5, that's going to be 11.5. Again, this product equals 0, and then the AY product equals to 172.5. Area number 3, okay, is 12 times 1.5, which is 18. The X component is 0. The Y component is 1.5 divided by 2, because we're going from here, from the center of, from the centroid of this rectangle here to the bottom of our chosen datum. So this is going to be 3/4 to do 0.75. Again, this product is 0, and then here we have 13.5. Okay, now for our formula requires us, we will need to know this sum, which is 43, and then the formula requires this sum here, which is 406. Okay, so X, the centroid, is the sum of AI XI over the sum of AI, resulting in, and of course, this sum here equals to 0. So here we'll have 0 over 43 equals 0. And now the YG equals to the same thing, the sum of AI YI equals to the sum of the areas, and we'll have 406 divided by 43, and this means that our Y component is going to be 944 inches. Okay, so what this means is that the centroid of this shape is located somewhere here, 944 inches up. Let me draw and show you. I'm going to draw another, go to the next page. And I want to draw what we have calculated so far. This is the point where our elastic neutral axis is. And this is the distance that we just have calculated, which is 944. And that means, because we know the entire length is given to us, is 22.5, meaning that this dimension here is 1306. And so knowing these dimensions, let's go and fill out every single space here. So this is 944. We know that this is 1.5. So 944 minus 1.5 equals 794. This here is 794. Same thing at the top here. We know that this thickness of the flange is 1, meaning that this dimension here is going to be 1206. Okay, now moving forward here, we need a dimension from the neutral axis through to the center of each shape. And let's see here. This one is going to be 1306 minus the half of this thickness of the flange thickness, which is going to be 1306 minus 0.5. We have 1256. Then let's move forward. We need the, now we'll have this distance here is going to be 944 minus 3/4 equals to 869. Good. Now we need the distance from this centroid, this rectangle centroid, to the neutral axis. And this is going to be 1206 divided by 2, 603. And here at the bottom, we have 794 divided by 2, just 397. Now that we know that, we can move forward and do our calculations. Since we have calculated the elastic neutral axis and we know its location, what that tells us is that our B from the formula equals to 0.75, to this dimension here, which is 0.75. So we also have found out now that B equals to 0.75. Let's move forward now and calculate the moment of inertia. Now, moment of inertia for a shape with an arbitrary chosen datum. Let's go ahead to our FE handbook and see what we can find. Let me write down here, just in case you don't know the formula. I know it, but I want to show you that we have these formulas available in case you don't know they're available. Let's see, moment of inertia. Inertia. And we have to be careful because I need the moment of inertia with the respect to an arbitrarily chosen datum. So let me move forward. Okay, here it is. So moment of inertia of an area about an axis is defined as the moment of inertia of the area about a parallel central axis plus a term equal to the area multiplied by the square of the perpendicular distance d, blah, blah, blah. So this is what we need. This is the formula that I'm going to use. And let's go back now. Let me write here the formula. Equals to Ix plus the area times d squared. Okay, in our case, we are calculating the moment of inertia about the neutral axis, which let me also note that this is area 1, this is area 2, this is area 3, this is area number 4. Okay, so the formula is BH to third over 12 plus A times D squared equals 2. And let's start with area number 1. And we have, maybe if you forgot, I would like to point out, or maybe I should just write down here, area is 10. From the previous calculations, I will bring up area number 1 is 10. Area number 2, we have 1206. 1206 times 0.75. We we have 9,045. Area number 3, I will have 794 times 0.75 equals to 5,955. And area number 4 equals to 18. So that being said, let's start. 10 times 1/3 over 12 plus area, which is 10, times the distance from its centroid to the neutral axis. We have it right here, which is 1256. Plus, let's go to the area number 2, and we'll have 0.75 times 1206 2/3 over 12 plus area, which is 9,045 times the distance from its centroid to the elastic neutral axis is 603. Plus area number 3 will have 0.75 times 794 2/3 over 12 plus the area, which is 5,9. I'm going to go here, 5,955 multiplied by 397. Plus, and area number 4, we have 12 times 1.5 to the 3rd over 12 plus the area is 18 times D, which is 869 equals. I want to point out the importance of having your drawing as clean and clear as possible, because this will eliminate any mistakes and will accelerate your calculations. Doing these calculations, and I want to point out another thing, you should be able, if you have your calculator, your scientific, one of the calculators that are approved on the exam, I have HP35S, you should be able to do these calculations without writing anything on a paper, if you know how properly to use it. Calculated this, you should be getting 3504.7 to the 4th. So now we also have calculated the moment of inertia. I will go ahead and move forward. Now, if we look at our formula, the next thing to calculate is the moment of area. So we know the moment of inertia equals to 3504.7. I'm going to put inches here. We'll have inches to. Now let's go ahead and calculate the moment of area. Let me point out one thing. So this neutral axis here, the point of neutral axis, divides this shape into 2 other shapes, and the moment of area of these 2 shapes is the same, meaning that in moving forward, you can calculate the moment of area of this shape or the moment of area of this shape to use in your calculations. So let's, I would like to calculate both, and I would like to show how they are equal. So let's note Q1. I'm going to take Q1 as the upper part, and I have A1, which is 10 times 1256 with the arm, and plus area number 2, which is 9,045 times 603 equals. Let's go ahead and calculate this. So I have 10 1256 multiply 9045 603 multiply plus. I'm getting 180.1. And this is inch to the third. This is 1. Let's go ahead and calculate the moment of area about the at the bottom side. I will have 5955 times 397 plus area number 4, which is 18 times the arm 869 equals. Again, let me quickly calculate this. We have 5.955, 397 multiply 18, 869 multiply plus. Again, I'm getting 180.1. All right, so we just verified that the moment of areas are the same. I just wanted to point out that they should be the same. If they're not, then there's probably a mistake somewhere. So now that we know everything in our calculations, let's go and calculate the shear stress, transverse shear stress. I will write the formula again. VQ over I times B equals 2. The shear force in the problem is 90 kips. Times Q, we have 180.1 inch to the third over moment of inertia, if you remember, is 3 moment of inertia is 3,504.7 inch to the 4 times B, and B is 0.75 inches. And we are going to get, we have 90, 180.1 multiply 3,504.7, 0.75, and divided. So we're getting 617 kips over inch squared. An important thing to note is that for an I shape, the flanges actually, they take very little shear stress. So we can actually calculate an approximate shear stress by considering only the web. Let's see if we do that, what are we getting? So we can calculate the shear stress by only considering the web using this formula, force over the area, the shear force over the area, and we will have 90 kips over the area of the web, which is 20 inches times 0.75. And this equals to, let me see, 20, 0.75 times, we're getting 15, 90 divided by 15, we're getting 6. So you see how the answer is very close to what we have calculated. We got 6.17, and we got an approximate shear stress by simplifying the calculations a lot. So this approximate shear stress can be an alternative for you to calculate the shear stress during the exam. That's it for today, my friends. I hope you found this video helpful. If you did, don't forget to subscribe and give it a like, because this helps people like you find me. Also, if you have an engineering degree from outside of the United States and you are interested in evaluating your education in this country, I have put together a PDF guide with step-by-step instructions on how to do just that. Just click the link below and you'll be able to download it for free. Keep up the good work, and I will see you next week.